February 2026, the bridge is finished. The bridge is standing. The bridge is silent. 6 years of construction, 6.4 billion Canadian dollars. 853 meters of steel suspended above the Detroit River. And on the day it was supposed to open, the world was arguing about it instead of crossing it. They built the longest cable-stayed bridge in North America. Then the president said no. Welcome back to the channel. Today we are telling the full story, not the political story, not the headline story. How two countries decided to build something that had never been built on this continent before. And how thousands of workers, over thousands of days, made that decision into something you can drive across. This is the Gordie Howe International Bridge. And this is how it was built. This is not just a bridge over a river. This is not just a convenient way to cross from Windsor, Ontario into Detroit, Michigan. This is North America's longest cable, stayed main span 853 meters of suspended deck, held in the air by 216 cables, anchored to 2 towers. This is a 6-lane international crossing, with a dedicated pedestrian and cycling path connecting Interstate 75 in the United States to Highway 401 in Canada. 2 of the most important freight corridors on the continent, joined at the hip above one river. The total length of the bridge structure is 2.5 kilometers. The deck clears the water by 46 meters, high enough for the largest commercial vessels that operate on the Great Lakes to pass underneath without slowing down. The deck is 37.5 meters wide. The towers, when complete, made the Canadian Tower the tallest structure in the city of Windsor. This is a megaproject by any definition of the word. But to understand why it exists, you need to understand what was there before. Before we go further, if you are new here, subscribe. We cover the largest, most complex engineering projects ever attempted. Hit the bell so you don't miss the next one, and stay until the end of this video, because the final phase of this bridge's construction story is one that almost no one is talking about. Now the blank canvas. For decades, there was one bridge, one crossing, one connection between the largest commercial land border corridor in North America. The Ambassador Bridge, opened in 1929, privately owned, a single span carrying an extraordinary share of the trade between the United States and Canada, around 8,000 trucks. Per Dalton Y, roughly 320, approximately a quarter of all land trade between the two countries, flowing through one structure built almost a century ago. The problem was not that the Ambassador Bridge was broken. It worked. It kept working, but a corridor this critical cannot depend on a single point of failure. One incident, an accident, a security alert, a severe winter storm, a structural issue, factories on both sides of the river, idle supply chains break. The economic consequences ripple outward faster than anyone can contain them. The argument for a second crossing had been building since the 1990s. Studies were commissioned, proposals were made, negotiations began. 20 years of planning, politics, and process before a single machine touched the ground. In May 2015, the Canadian government announced the name, the Gordie Howe International Bridge, named for the man who played 25 seasons for the Detroit Red Wings. The man they called Mr. Hobby, a name that belongs to both sides of the river. On the 28th of September 2018, the contract was signed. The consortium bridging North America, selected through international competitive tender on the 5th of July. 2018 became the design, build, finance, operate, maintain partner. The fixed contract value, 5.7 billion Canadian dollars for construction and long-term operations. And in October 2018, the first machines arrived on site. The blank canvas was ready to be filled. But before anything goes up, you have to understand what is beneath your feet. In the case of the Gordie Howe Bridge, what was beneath the engineering team's feet was complicated. The Detroit River is not just a river. It is a busy international waterway connecting Lake St. Clair to Lake Erie, carrying heavy commercial vessel traffic year-round. The riverbed is layered, soft sediments at the surface, then clay, then limestone, then bedrock at depth. The geology on the American side is not identical to the geology on the Canadian side. The two main tower foundations would be sitting on different ground conditions, different depths to bedrock, different load-bearing characteristics, and yet they would have to work together as a single structural system. Before design could be finalized, before contracts could be fully priced, the ground had to be understood. Geotechnical investigation crews went to work. Boreholes were drilled into the riverbed and the shoreline on both sides. Core samples were extracted and analyzed. Layer by layer, the composition of the ground was mapped. The depth to bedrock was measured at dozens of points across the project footprint. The bearing capacity of different strata was tested. The history of both sites was examined for contamination, buried structures, old industrial fill, anything that might complicate or compromise the foundations that would eventually be placed there, because a tower 220 meters tall is not something you guess about. The loads involved are staggering. The self-weight of the tower, the weight of 216 cables pulling from every angle, the weight of the entire suspended deck and everything on it. The dynamic loads of traffic moving across it continuously. The wind loads, all of that force, concentrated, multiplied, directed lands on the foundation. The foundation cannot move. It cannot settle unevenly. It cannot shift under load. It has to be as close to immovable as human engineering can make it. The solution on both sides was deep foundation piles, steel and concrete piles driven or drilled into the ground to reach bedrock, creating a network of load transfer points that would eventually be tied together by massive pile caps. Reinforced concrete elements sitting at or near ground level, distributing the tower load across all the piers. It is loud, it is slow, it is methodical. Drilling rigs positioned over each pile. Location, boring through overburden, through clay, through softer rock, until the bit reached the competent limestone below. The borehole cleaned out, steel reinforcement cages lowered, in concrete pumped down from the surface. Each pile a separate operation, each pile verified. There were dozens of them per tower. The work continued for months. Every millimeter of pile position mattered. Every concrete mix was tested. Every pour was monitored for temperature, because concrete cures through a chemical reaction. In cold weather, the freshly placed concrete had to be protected from freezing, wrapped in insulating blankets, sometimes heated until it gained enough strength to survive on its own. In summer heat, the reaction could run too fast, creating internal stresses that weaken the finished product. Then came the pile caps and the foundation slabs. Massive reinforced concrete platforms tying all the piles together into a unified system. The formwork for these elements was engineered in itself. Complex, three-dimensional wooden and steel frameworks holding the shape of the future concrete until it could hold its own shape. Inside the formwork, steel reinforcing bars were assembled in precise geometric arrangements, tied by hand, checked against structural drawings, inspected before a single cubic meter of concrete was poured. The concrete volumes for the two tower foundations were enormous. Concrete arrived in mixer trucks, truck after truck, rotating continuously to keep the mix from setting before it reached the forms. The pours for large foundation elements often had to be continuous. Once started, they couldn't be stopped midway because a cold joint in a major structural element creates a plane of weakness. Teams worked in shifts. Concrete was pumped to height, placed by workers with vibrators. Every sample was tested. Cylinders of concrete were kept and crushed at regular intervals to verify that the material had achieved its design strength. While the foundations were taking shape, the approach structures were being prepared on both shores. These are the elevated roadway sections that connect the main bridge. They required their own pile foundations, their own bridge piers, their own deck construction. They were designed to integrate CAN with the main bridge at one end and with the toll plaza and port of entry structures at the other. This work ran in parallel with the tower foundation, multiple simultaneous construction, fronts coordinated across an international boundary, and then the towers began to rise. The two towers of the Gordie Howe Bridge are a frame structures, not a rectangular column, not an H-frame, two inclined legs that converge at a shared apex 220 meters above the river. The choice of form is not arbitrary. The A-frame geometry creates an inherently stable shape for resisting the asymmetric cable loads that come from different directions as traffic patterns vary across the deck. It also produces the distinctive visual signature that defines the bridge identity on the skyline of both cities. Each tower was divided into construction segments, individual pieces of formwork that defined the geometry of one lift of concrete at a time. The sequence went like this: set the formwork for the next segment, position the reinforcing steel inside, pour the concrete, wait for it to cure to the required strength, strip the formwork, move it up to the next level, on and on, meter by meter, from river level toward the sky. The complexity of the A-frame geometry made each segment slightly different from the one below it. As the two legs of the tower converged toward the apex, the angle of the formwork changed. The reinforcing arrangements changed. The connection details between segments evolved. The engineering team had modeled every segment before construction began. On site, surveyors checked the geometry of each completed level before the next was started. The position, the inclination, the alignment. Any deviation had to be caught early before it compounded. Getting material to height was a logistical challenge that grew with every level. Reinforcing steel, hundreds of tons of it over the full tower height, had to be lifted, sorted, and placed at elevation. Concrete had to be pumped from ground level to the active formwork, sometimes more than 100 meters up. The pump lines grew longer as the tower grew taller. Pump pressures increased. Concrete mix designs were adjusted to remain pumpable at the pressures required. Cranes were the central infrastructure of the tower construction phase. Large tower cranes anchored to the bases of the towers with their own climbing mechanisms, rose with the construction, always staying within effective working height of the active work level. The selection of crane size, position, and climbing sequence was itself a detailed engineering exercise. Cranes that are too small can to lift the loads. Cranes that are too large may be impractical to erect or dismantle. And the geometry of two converging tower legs creates interference zones. At 200 meters above the river, the wind environment is fundamentally different from ground level. Not just stronger, more variable, more turbulent, more directionally complex. Operations with large suspended loads, whether a reinforcing cage, a formwork panel, or a concrete pump line. When wind exceeded those limits, lifts stopped, the work waited, then resumed. The schedule had to absorb these interruptions. Day after day, season after season, the towers grew through 2019, through 2020, through 2021. COVID-19 arrived in North America in March 2020 and hit construction sites hard. The Gordie Howe project was not immune. Site access was restricted as health protocols were implemented. The peak workforce of up to 2,000 workers per Dalton Y had to be managed with new distancing requirements. New site organization, supply chains for materials and equipment were disrupted globally, lead times lengthened, deliveries were delayed. Certain items became difficult to source. The project's schedule, which had originally targeted completion by late 2024, began to slip. The pandemic added approximately 700 million Canadian dollars. The schedule moved first to late 2025, then to early 2026. But the towers kept rising. In December 2023, both towers reached their full design height of 220 meters, a milestone that the construction team had been working toward for 5 years. The skylines of both Windsor and Detroit had changed permanently. Then came the cables. The cable stay system is the defining structural element of a cable. Stayed bridge. The bridge does not work without it. The deck does not hang in the air without it. 216 individual stay cables, each one a precisely engineered element connecting a specific point on the deck to a specific anchor location on the tower. Each stay cable is composed of multiple parallel steel strands, high-strength pre-stressing steel. Each strand itself made of multiple individual wires. The strands are bundled together inside a protective outer sheathing, typically high-density polyethylene, colored to reflect heat and resist UV degradation. The sheathing is also designed to manage rain, wind, induced vibration, a phenomenon where water flowing along an inclined cable in wind can induce oscillations that fatigue the cable over time. The cable geometry, the sheathing surface, the anchorage damping systems, all of these are designed together to prevent that failure mode. Installing the cables required work at both ends simultaneously. Anchor points in the tower. The deck anchor points were similarly built in during deck fabrication, because the deck had not yet been built when the towers were completed. The deck of the Gordie Howe Bridge was constructed as a steel box girder composite system, a series of prefabricated steel sections, each manufactured in a controlled factory environment, transported to the site, lifted into position by cranes, connected to the previous section. Deck construction began from both shores and worked toward the middle. From the American abutment, the deck sections advanced over the river, each new section cantilevering out beyond the last, held in position by the cable system as it was built out. Simultaneously, from the Canadian abutment, the same process advanced from the other direction. This method, balanced or staged cantilever construction, is the standard approach for cable. Stage spans, but that does not make it simple. The structural state of the bridge changes with every new section added. The forces in every existing cable change when the next deck section is placed. Every step of the construction sequence has to be analyzed for its effect on the whole system, and the cable installation tensions have to be adjusted accordingly, so that when the final connection is made and the bridge reaches its complete form, every element is carrying exactly the load it was designed to carry, no more, no less. The precision required is measured in millimeters. The deck has to arrive at the mid-span connection point at exactly the right elevation, with exactly the right geometry, so that the final closure segment can be installed without forcing. To achieve this, the construction team used detailed geometry control surveys. At each stage, the actual positions of the deck ends were measured and compared to the theoretical positions from the construction model. If deviations were found, they were corrected by adjusting cable tensions before the next section was added. The model was updated, the real structure was adjusted, and the two were kept in agreement throughout. The fabricated steel deck sections were themselves complex manufactured components. Each section was a welded steel box, top flange, bottom flange, longitudinal web plates, internal transverse diaphragms, stiffening elements. The dimensions were precise to fractions of a millimeter. The surface preparation and coating were applied in the factory environment, where quality control is far more reliable than it would be on an open construction site over a river in winter. Transportation from fabrication facilities to the site required careful logistics. Sections were moved by truck and barge. On site, the sections were lifted by large derrick cranes positioned on the completed deck sections behind them, cranes that themselves had to be rated for the loads involved and positioned to avoid overstressing the deck structure they were standing on. The cables were installed in stages. As the deck advanced, each pair of cables, one from each side of the deck to the tower, was stressed to an initial tension, then adjusted as subsequent deck sections and cables were added. The stressing sequence was carefully planned to manage the distribution of forces across the entire structure. Throughout construction, the stressing hardware, hydraulic jacks, precision load cells, anchoring components. By mid-2024, the two deck fronts were close to meeting. The main span over the International Navigation Channel was nearly complete, and on the 14th of June, 2024, the two halves of the deck were joined above the Detroit River. The American side met the Canadian side in the air above the water. The final cable connections were made. The main structure of the bridge was physically complete, but a bridge structure is not a bridge in service. After the structural closure, the work on the deck surface began. The steel deck needs a wearing surface, a sophisticated pavement system designed for the specific challenges of a bridge environment. They expand in summer heat and contract in winter cold. They flex under traffic loads. The pavement system has to accommodate all of this movement without cracking, without delaminating, without creating drainage problems. The systems used on the Gordie Howe deck were specially formulated for bridge applications different from standard highway asphalt. Then, the road markings, the barrier systems, the median dividers separating the 6 lanes of traffic, the pedestrian and cycling path along one side of the deck, separated from vehicle traffic by its own barrier system, the lighting infrastructure, hundreds of poles positioned at engineered intervals to provide the required illumination. This is one of the elements that most people driving across the bridge will never think about. But it is one of the most sophisticated aspects of the whole project. Hundreds of sensors embedded in the structure throughout construction, strain gauges, in the steel and concrete, vibration sensors, all of these feeding data in real time to a central monitoring system. The health of the bridge is observed continuously, and the data is compared against the design predictions. If the structure behaves unexpectedly, If a cable shows unusual vibration, if a strain reading trends in the wrong direction, the monitoring system flags it. Without this system, anomalies could go undetected for months. With it, the engineering team knows the state of the bridge every minute of every day. Then the toll and traffic management systems. The Gordie Howe Bridge uses a free-flow electronic tolling approach, no traditional toll booths. Gantry, mounted cameras and transponder readers capture vehicle information as traffic moves at speed. The system integrates with tolling networks from both countries. The back office processing handles billing, enforcement, account management. Testing this system required running realistic traffic scenarios before opening, verifying that the hardware and software performed correctly across the full range of vehicle, then the ports of entry. This is infrastructure that has no equivalent on a domestic bridge. The full customs and border protection facilities required for an international crossing. On the Canadian side, the Canadian Border Services Agency facility. On the American side, the U.S. Customs and Border Protection Facility. These are not small buildings with a few booths. They are large-scale processing facilities with vehicle inspection lanes, commercial truck inspection bays, primary and secondary examination areas, administrative and operational spaces, vehicle marshalling areas, and all the IT infrastructure required to connect with the border management systems of both federal governments. The design and construction of the ports of entry had to be coordinated with the operational requirements of the border agencies, who had their own standards, their own security requirements. Testing the ports of entry involved not just building systems, but joint operational exercises, running simulated traffic through the facilities, testing the physical inspection equipment, training the staff who would actually work there, the drainage system. Invisible to every driver, water falling on the deck has to go somewhere, and on a bridge, it cannot simply soak into the ground. The deck drainage system collects surface water through a series of drains at engineered intervals, carries it through down pipes inside the structure, and routes it to treatment or discharge points that comply with environmental requirements. Steel exposed to water is steel that corrodes the drainage system, protects the structure. The fire suppression, the traffic management control center, where operators can monitor the bridge and respond to incidents. The variable message signs that can communicate information to approaching drivers. The CCTV coverage of every lane, every square meter of the bridge deck, and approaches. Everyone was verified against its specifications before the project team was willing to say, "This bridge is ready." Load testing. In the final stages before opening, the bridge went through formal load testing. Heavy vehicles placed in specific positions. The measured behavior of the bridge under these loads was compared directly to the predictions of the structural analysis model. The agreement between prediction and measurement is the final engineering proof that the bridge was built as designed. The agreement was found, the model was validated, the structure performed as calculated. In February 2026, with the bridge ready to open, a geopolitical argument over trade between the United States and Canada briefly turned this structure into a political flashpoint. The details filled newspapers and social media for a few weeks, but the bridge itself remains standing around it. 853 meters of steel does not care about a post on a social network. ID. The bridge is the 10th longest cable stayed main span in the world. It is the longest cable stayed main span in North America by a significant margin, and it was built by thousands of people over more than 6 years, in conditions that ranged from the ordinary challenges of large-scale construction to the extraordinary disruption of a global pandemic. Most people who drive across the Gordie Howe Bridge will see two towers. They will see the Detroit River below them, 46 meters down, and perhaps a freighter heading toward the lake. They will see the skylines of Windsor and Detroit. They will not see the hundreds of piles drilled to bedrock under the river. They will not see the thousands of tons of reinforcing steel cast into the concrete of the two towers. They will not see the 216 individual cables, each tensioned to a precise load, carrying the deck in tension toward the sky. They will not see the drain pipes inside the deck structure, carrying water away from the steel. They will not see the hundreds of sensors reading the bridge's internal state in real time. They will not see the years of geotechnical investigation that preceded the first concrete pour. They will not see the nights in February when workers were heating freshly poured concrete so it would cure correctly in the Canadian winter. They will not see the cable-stressing crews working at height in the wind, adjusting tensions to fractions of a percent. They will not see the months that the global supply chain failed them. And they found another way. They will not see the 2,000 people who showed up every day for years and built something that had never been built on this continent. They will just see the bridge, and the bridge will be enough. But now you know what it took. Gordie Howe played hockey for 25 seasons. He didn't get the name Mr. Hockey from one good game or one good year. He earned it through decades of showing up when it was hard, when it was painful, when it would have been easier to stop. The bridge that bears his name was not built in one good year either. It was built through supply chain failures and pandemic shutdowns and schedule slips and cost overruns and political friction and thousands of days of ordinary work by people who showed up anyway. Without those people, there is no bridge. With those people, there is 853 meters of the longest cable, stayed main span in North America, standing 46 meters above the Detroit River, connecting two countries, carrying the weight of a continent. That is what it means to build something. If you found this video worthwhile, subscribe to the channel, hit the like button, and leave a comment. What mega project do you want us to cover next? We read every suggestion. Coming up, the Ambassador Bridge, 96 years old, still carrying a quarter of US. Canada land trade, privately owned. And its own story is one that most people don't know. Thank you for watching.